Hello students, welcome back. Let us resume our discussion in section 2. Previously, we completed 2.2 quadratic residue condition, or Euler's criterion. If P is an odd prime and P does not divide A, and the second condition, P does not divide A, means the same as A is non-zero modulo P, then A is a quadratic residue of P if and only if, and then here comes Euler's criterion. A to the P minus 1 over 2 power is congruent to 1 modulo P. And this is necessary and sufficient condition. So if yes, then a quadratic residue. If no, then it is a non-residue. By the way, P is an odd prime, so this P minus 1 is even. So P minus 1 divided by 2 is a positive integer, so A to that power, P minus 1 over 2 power, is well defined. No problem there. And that's what we did as the first half of this Euler's criterion. And here comes the second. Under the same condition, P is an odd prime and P is not divide A. In other words, A is non-zero mod P. Then A to the P minus 1 over 2 power is either 1 or negative 1. Either one or the other, nothing else. So in this case, congruent to 1, then that's the same as Euler's criterion here. So we have quadratic residue. A is a quadratic residue. If the latter, then it's a quadratic non-residue. And of course, there is a singular case. A is non-zero. So what if A is 0? Well, 0 is 0. That's separate. And by the way, let me emphasize once more. A is non-zero, and P does not divide A. These two mean the same thing. And also, P and A are relative prime. All those three mean the same thing. Okay, alright, that's what we did last time. And let's continue on. Here's a corollary of the previous theorem. P is an odd prime, and R is a primitive root of P. Wait a minute, do you remember primitive root? Yeah, here's a review. So primitive root, A and M are relative prime, but this time we are doing modulo prime. So A and P are relative prime, which means, yeah, the same as P does not divide A, also the same as A is non-zero mod P. So this one here, at least the P version, is equivalent for this one, and that one. And then here's the key part. The order of A modulo P is phi of P. That's when we have a primitive root of unity modulo P, or simply a primitive root of P. We are doing modulo prime, so we are replacing all M into P. Otherwise, this definition is perfect. Come back to this. That's what this primitive root of P is talking about. Then R to the 2k power is a quadratic residue, and then R to the odd power is a non-residue. Where's the proof? Well, the proof for the quadratic residue is just too simple. If you simply take R to the k power and that's it. Detail is left to the students. Now, what if you have R to the 2k plus 1 power? In that case, let us put it into Euler's criterion, A to the P minus 1 over 2 power, and let's work it out. Let's see. We have to look at this power, so maybe it's going to be better if I expand the font. Okay, alright. Didn't look pretty. It doesn't look pretty. Let's go back. Let me copy and paste this thing here. And then let's see. Shall I expand the font? Okay, alright. That's much better. So A to the P minus 1 over 2 power. And A is R to the odd power. That's assumption, so let's do that. And then we can decompose r to the 2k plus 1 power into r to the 2k power times r to the 1 power. And then we distribute the powers. It's an exponent rule. If you have same power and then two different bases, the powers are distributed over. So r to the k p minus 1 power, because 2k and then this 2 in denominator cancels each other out. And then we have r to the p minus 1 over 2 power. Alright, and this one here, r to the p minus 1 to the k power. Yeah, just another exponent rule. Multiplication is commutative, so you can change the order. And then this one, alright, r to the p minus over 2 power. Now this one here, that's 1. R to the p minus 1 power is 1 because of Fermat's theorem. P minus 1 is phi, so I should have said Euler Fermat's theorem. So this is basically 1 to the k power times, yeah, alright. So this is just r to the p minus 1 over 2 power. And then finally look at this. R to the p minus 1 over 2 power cannot be congruent to 1, I claim, because r is a primitive root of p. It's a primitive root of p, so the modular order has to be p minus 1, but this is less than p minus 1. You see? Go back to this definition of primitive root. The order of a modulo p must be equal to phi of p. That's a condition for primitive roots. Remember, we are doing modulo prime, so all m's are translated into p. So we want phi of p, which is p minus 1. Here, instead of p minus 1, we have only half of that. And this is primitive root, so this should not be congruent to 1. Remember, the order, the modular order, the order of a mod p is the minimum, the smallest integer such that a to the certain power, certain positive integer power, is congruent to 1. It's the smallest positive integer. And the smallest positive integer is p minus 1, and this is less than the minimum, so we cannot have 1. So it's not 1, so it has to be a quadratic non-residue. So what did you get? Even power, quadratic residue. Odd power, a quadratic non-residue. And consequently, we have to have the equal number of quadratic residue and quadratic non-residue here. So all integers can be classified into the primitive root to a certain power. And then 1 power, second power, third power up to phi of p power. P minus 1 power, there are that many of them. And then among them, even powers are quadratic residues and odd powers are quadratic non-residues. There are total p minus 1 of them. So half of them are quadratic residue and the other half are quadratic non-residue. And then there is 0, so half of p minus 1, the other half of p minus 1, and then plus 1 add up to p. Let's see, do we have an example problem here? Determine all quadratic residues and non-residues modulo 13. Okay, we can use this Euler's criterion, this one right here. Or maybe this one is a bit easier. So a to the p minus 1 over 2 power is either 1 or negative 1. 1, then quadratic residue. Negative 1, then quadratic non-residue. So we can check all those manually, one after another. P minus 1 over 2 is 6 in this case. 13 minus 1 over 2 is 6. So here are the computations of a to the 6th power. 1 to the 6th power is easy. 2 to the 6th power, I did here 2 to the 3rd power first and then square, but 8 is congruent to 5. 5 squared is 25. 26 minus 1, so that's congruent to -1. So, yep, okay, that's a quadratic residue, and this one is non-residue. 3 to the 6th power, 3 to the 3rd power, and then square, and then 27 is 26 plus 1, so that's 1. So that's quadratic residue. How about 4 to the 6th power? We already did 2 to the 6th power, and that square, -1 squared, is +1. So that's quadratic residue. And then we can complete all those computations with various uses of congruence and exponent rules, whatnot, to calculate. You can, of course, do those brute force method. Eventually, we get the same number of quadratic residues and quadratic non-residues. Yes, they all have to be the same, as you saw from this corollary. No, not this one. Where's the corollary? P minus 1 over 2 and P minus 1 over 2. So 6 quadratic residues and 6 quadratic non-residue, and then 0, adding up to 13 total. Here's a verification, and in this verification I did just brute force computation with Mathematica. A to the P minus 1 over 2 power, just calculate that and then did the mod operation and then list them all. We have 1, 1, 2, 12, which is -1, 3, 1, 4, 1, 5, 12, which is -1, and so on and so forth. And then select those with congruent to 1, those are quadratic residues, and those are congruent to -1, those are quadratic non-residues. And then we have 0. Alright, including the examples, we completed section 2. Let's meet again in lesson 14.